Okay, everybody, we're going to continue on with Chapter 7 and start looking at substitution, reactions of haloalkanes. That's the next piece that we're going to talk about in this course. So let me start sharing my screen. Okay, so remember my X is halogen. So on this slide, I have alkyl halides indicated. Now, in this top example, an alkyl halide undergoes a substitution reaction. So my halogen gets substituted by another group when it reacts with a nucleophile. So whatever this nucleophile is, it actually forms a new carbon-carbon bond and ends up substituting the halogen with this group. And I get this halide ion because the halide ion actually leaves and I have a substitution reaction. Now, I can also undergo an elimination reaction if I have a base here. So if I look at this, right, this is my alpha carbon, this is my beta carbon. If I have a hydrogen on that beta carbon, I'm going to get minus HX. So again, the opposite of that hydrohalogenation addition reaction to alkenes. I'm going to get the base, the conjugate, and I'm going to get the alkene, the conjugate acid of the base, and I also get halide ion in this reaction. Now, in order to determine whether my alkyl halide undergoes substitution and elimination, we have to think about what nucleophiles and bases actually have in common. What we know is that some reagents can act as a nucleophile or a base. And when this happens, elimination and substitution will be competing reaction pathways. So here, I have my OH minus. This can be a nucleophile. This can also be a base. We've seen hydroxide as a base. So what's happening here is I can get an elimination product where the HCl is eliminated, or I can get a substitution where my chlorine is actually replaced, and what I have is the formation of a new carbon-oxygen bond, because this is actually reacting as a nucleophile in this particular reaction. So the hydroxide acts as a nucleophile and can undergo substitution. The hydroxide can also act as a base and undergo elimination. So what causes it to do one or the other? That's the trick to this section of the course. There are two main reasons why alkyl halides undergo substitution and elimination reactions. So let's start looking at the beginning so we can try to figure out the basis of these two reactions. I know that the halogen is electron withdrawing. So this creates that partial positive charge on that alpha carbon. That alpha carbon becomes electrophilic or electron poor, which makes it susceptible to nucleophilic attack. Remember, my nucleophile is going to be electron rich, an area of electron density. So this area of electron density can actually attack the carbon. And my halogen, right, these electrons can leave, and I end up with a new bond between my nucleophile and my carbon, right? This is the bond that's going to be made. This is the bond that's going to be broken. So the halogen acts as a leaving group because it leaves. And for a substrate to undergo a substitution or an elimination reactions, I have to possess a good leaving group. In the following general reaction, notice that my carbon that undergoes substitution, right, that carbon is an sp3 or tetrahedral carbon. And my nucleophile actually is going to replace, right? This is going to come in and this is going to leave, and I form this new nucleophile carbon bond, and I have the X as a leaving group because it's leaving. So this is called nucleophilic substitution because the nucleophile is attacking the carbon and the carbon halogen bond ends up breaking and a carbon nucleophile bond ends up forming. So in my nucleophilic substitution, my nucleophile displaces. Now notice this terminology. It displaces the leaving group on the substrate. So my alkyl halide, this is going to be the substrate. My nucleophile is going to be some electron rich, I'm looking at negative, partial negative, and lone pairs in order to act as a nucleophile. My substrate has to have an electrophilic carbon because I have to have an electron core area for that nucleophile. I just wrote poop. Core area for that nucleophile to attack. So I'm forming this new carbon nucleophile bond, and I'm breaking the carbon halogen bond. So remember what my nucleophile is. It's a Lewis base or an electron pair donor. It's neutral in that it has a lone pair, or it can be negatively charged. My leaving group is a species that actually takes a pair of electrons with it, right? These electrons end up on the halogen. So those electrons end up on the halogen when that bond breaks. So the leaving group takes the electrons and leaves. Here's an example of these nucleophilic substitution reactions. So here I have examples of the nucleophile. And remember, I'm going to have the nucleophile forming a carbon nucleophile bond. So when the nucleophile is hydroxide, right, I form a carbon oxygen bond, whatever was on that carbon is still there, but that's going to form an alcohol directly. If I have an alkoxide, so this is hydroxide, this is an alkoxide, where I have an R that's attached to the O, and I still have that negative charge. So this is the bond that's being made, right? I have the carbon, and then I'm reacting with that OR, so I get an ether. This can happen with an SH minus, remember sulfur is like hydroxide. It's going to have a little bit larger, sulfur atom is a little bit larger, which is going to come into play. But I make a thiol here because I'm forming the carbon SH bond, similar to making the alcohol. This is sort of the counterpart to the alkoxide. I make this sort of thiol ether, right, which is called a sulfide, as we learned, or maybe we will learn. So again, I'm forming this carbon-carbon bond, and the thing that's replacing the halogen is that nucleophile. I could also have an iodide ion replacing that other halogen. Iodide will actually replace bromine and chlorines. So there's reasons for that you may or may not know, but I form that carbon iodide bond because iodide is that nucleophile. So now notice that these are all negatively charged species. And when I have them sort of replace the halogen, I end up with neutral products formed. I can also have nucleophilicity. These are nucleophiles because they have lone pairs, which are also areas of electron density. So it's the lone pair that is actually doing the reaction and attacking that carbon. So here, if I look at NH3, here's my nucleophile, right? That lone pair, and then my carbon. This is going to make that bond, and what I get is this HC, H, H, and then here I have this charged species, and then I have my X minus, sort of as that counter ion. So these actually have to undergo a deprotonation step, similarly to what we saw before with when I protonated an alcohol and the alcohol came in and reacted with was electrophilic, and then I ended up with the water or the ether, right? The water or the alkoxide reacting with the carbocation, and then I had a deprotonation step. These products, right, will form neutral products after a deprotonation step in their mechanism. So these are all charged species, but what's going to happen is those nucleophiles are going to act sort of as bases and do a final deprotonation step. So I'm going to get the amine, the alcohol, and the ether, and I get them after a deprotonation step in the mechanism. So I don't actually isolate this charged species. I do have those nucleophilic species are going to end up deprotonating this intermediarily charged product, and I end up with either the amine, the alcohol, or the ether as the final product. Okay. So now comes the fun part. There are two possible mechanisms for nucleophilic substitution. I have a concerted mechanism, or I have a stepwise mechanism. Let's look at the concerted mechanism first. This involves the breaking of the bond to the leaving group and the making of the bond to the nucleophile at the same time. So this nucleophile is coming in and this leaving group is leaving at the same time. It's concerted. It's happening at the same time. So I am forming this bond and I'm breaking that bond at the same time. The nucleophile attacks the carbon, the halogen leaves at the same time. So I have both nucleophilic attack and the loss of the leaving group happening together simultaneously. The nucleophile attacks the carbon, that causes the leaving group to leave, and I form the bond and break the bond in simultaneously or in a concerted fashion. The stepwise mechanism has the leaving group leaves first. I get an intermediary carbocation, and then I have nucleophilic attack. So this bond is broken first. The leaving group leaves, which gives me this carbocation, right? This is a carbocation intermediate because I only have those three groups attached to that carbon and I have a positive charge. Then the nucleophile comes in a separate step and makes the new covalent bond. So here in my second step, this is step 1, this is step 2. This ends up having a bond breaking first to form the carbocation. That's a separate step in the reaction mechanism. And then in the second step of the reaction mechanism, the nucleophile is going to come in and form that new covalent bond between itself and the carbon that bears a positive charge. So the fact that this undergoes the carbocation intermediate means I'm subject to everything you learned about carbocations. Specifically, I can have rearrangements when I form a carbocation. So you have to watch out for that as well. Now, this is called the concerted mechanism. It's called an SN2 mechanism. So this is substitution nucleophilic bimolecular. So substitution nucleophilic, the 2 refers to bimolecular because 2 species are involved in the rate determining step. So the rate of this reaction is dependent on both the concentration of the alkyl halide and the concentration of the nucleophile. Remember, these brackets are equal to molarity, which is equal to moles per liter, which is a concentration. We're really not going to focus on calculating with this. What you should know is that this kinetic result, which is this rate, is one of the ways we know as scientists that this is a concerted one-step mechanism where those two processes, the attack of the nucleophile and the loss of the leaving group, take place simultaneously. What that means is that both of the reactants are involved in the transition state of the rate determining step. So you need to know how to draw this. Because this is actually the mechanism showing that transition state. So this is my nucleophile. This is my substrate. My bromine is my leaving group. Here's my electrophilic carbon. So notice in the transition state, right, I have this bond and this kind of partial bond. The HO carbon is partially formed, and the carbon bromine is partially broken. So I have a partial negative and a partial negative because these electrons are still kind of on the oxygen, and these electrons are sort of leaving to the bromine. So I have this partial negative, partial negative. My central carbon, this is sort of this triangular sort of geometry as something comes in. And it's sort of, notice it's sort of flipping like an umbrella. Here is where I have my tetrahedron. And now notice the OH is on the opposite side. So if that's a stereocenter, what I have is inversion of that reaction center. So if this carbon would be a stereocenter, it's not when I have all hydrogens. But if it were, if something was S, it goes to R. If something was R, it goes to S. This is called backside attack. My nucleophile is attacking on the opposite side of the carbon from where the leaving group is. So that's going to be this backside attack, which, if that is a stereochemical center, I get inversion of the stereochemistry. So let's look at this a little bit more. I have my negative OH minus, which is my nucleophile, bringing an electron pair to my partially positive carbon. The bromine begins to move away with an electron pair. So I get this transition state. This little double thing is indicative of a transition state. If you see that, what you're saying is this is a transition state. Remember, transition states are energy maximum on the energy diagram. You can't isolate a transition state. It's just sort of what's happening during the reaction in terms of my bonds making and breaking. So I have a partial bond, right? This carbon-oxygen bond is partially formed, and the carbon-bromine bond is partially broken. And because this is on the opposite side here, my configuration of that carbon, if it is a stereocenter, begins to invert. Here in my product, right, this is my product, my oxygen-carbon bond is formed, the bromine has left, and if that is a stereocenter, that configuration on that carbon has been inverted. So you need to be able to draw out this mechanism when, if I ask you for a mechanism of an SN2 reaction, or I ask you the mechanism of a reaction, and then you have to determine that it's SN2, and then you have to draw this type of reaction in the reaction question. Now, this is a one-step reaction because everything happens simultaneously, right? So I have one hump, I have one energy of activation. There's only one step, so that one step is the rate determining step. At this energy maximum, I have this transition state. This would be an exothermic reaction because the products are lower in energy than the reactants. So this is an energy diagram that you see routinely for SN2 reactions because I have one transition state and no reactive intermediate. Okay. This is going to be my stepwise mechanism. In the other mechanism, the bond breaking between the carbon and the leaving group is entirely completed before the bond break forming with the nucleophile begins. So this is why it's stepwise. I have bond breaking first. This is step 1 as the leaving group leaves. And then I have bond forming with the nucleophile as my separate step. So this is called an SN1, substitution nucleophilic unimolecular. Substitution nucleophilic unimolecular. Only my alkyl halide is involved in the rate determining step. The rate determining step is actually formation of the carbocation. That is the slowest step in this two-step mechanism. So I only have this rate being determined or being dependent on the concentration of the alkane. Once the carbocation forms, the nucleophile comes in and reacts. That happens fast. So it doesn't matter how much of that I have around because the rate is going to be determined by the consumption of the haloalkane. It's going to be determined by how quickly the carbocation is going to form. So this is going to be an illustration of an example of this SN1 mechanism. This is called solvolysis. In a solvolysis reaction, the solvent is going to act as the nucleophile. And I have terbutyl bromide, and then methanol is going to be the solvent and is also the nucleophile by virtue of those lone pair. So the first step in this is the leaving group leaves, right? The leaving group leaves, and I end up in this case with a tertiary carbocation because this carbon is attached to 3 other carbocation or carbon species. So this is going to be my tertiary carbocation. Remember, this is sp2 hybridized, it's trigonoplanar, it's flat, which has some ramifications later. And then this is my leaving group, which is now left. So the leaving group leaves, and I end up with the carbocation. So this is what's forming here. Step 2 is the reaction of the nucleophile and the electrophile to form a new covalent bond. But remember, this has my empty p orbital. My nucleophile can come in from the left or it come in from the right. The location of those 2 lobes of that empty p orbital allow for the nucleophile to attack from either face. It can come in from the right, it can come in from the left. So I can form this bond, which is from the left, and I can form this bond, which is from the right. What happens is I get 2 products. If this is a stereocenter here, I will get stereoisomers. If that carbon is a stereocenter. So what I would get here is here's one enantiomer. Here's the second enantiomer. This would form as a 1-to-1 racemic mixture. which means if this carbon initially had a stereocenter, I have now abolished it, and I have both an equal amount of each enantiomer that is possible. If I have an existing chiral center, I will racemize the center that actually is in the reactive center, right? If my bond doesn't break or form to the chiral carbon that is not part of the reaction remains unchanged. So if there is another chiral center in the molecule, and this chiral center is the reacting chiral center, I end up with diastereomers. We'll probably talk about that in more detail. Now, this is where I get this charged intermediate, and this is what I was talking about. I still have more methanol around, so this here is acting as a base, and that is picking off this protonation. I have this deprotonation step to complete the reaction, and I end up with my neutral ether in this case. Plus, I have this protonated alcohol, which is ready for another round. Now, this is a two-step mechanism in general. My SN2 reactions are going to be two steps. I have two transition states. I have one intermediate, which is my carbocation, at my energy minimum, or my localized energy minimum. This would still be a exothermic reaction because my products are lower in energy than my reactants. So this has a larger, right there, I have energy of activation 1, right? My larger EA is going to be for my rate determining step. That energy of activation is higher, so it's harder to get over. So that's going to control the rate of the entire reaction. As soon as a carbocation forms, boom, it's going to react because that energy of activation is markedly lower. This is my rate determining step. So this would be step 1, and then this would be step 2, just as we saw in the first part of chapter 5. Now this reaction, as drawn here, would have another hump. So I might see something like that, because this would be the deprotonation step. And it would actually be a 3-step mechanism, as indicated here, which wouldn't be rate determining. This deprotonation happens really, really, really fast. So it would have the shortest energy of activation, and then it would go really, really quickly. But if you had to draw an energy diagram for something like this, there would be that third deprotonation hump, that third step in the energy diagram. Now, let's talk about the fact that SN1 reactions occur where I have carbocations. One of the things carbocations can do is to rearrange. So you need to look for rearrangements when they happen. So this is an example. This bromine leaves. This is a secondary carbocation, but this can rearrange, and if it does, I form a tertiary carbocation. Remember, tertiary carbocations are much more stable than secondary. So this actually doesn't react, and if it does, it forms a very minor product. This is going to form the major product because this is more stable. And then what I'm going to have is my nucleophile is going to attack the tertiary carbocation, and then I have this last deprotonation step. So I have the major product being the product of a rearrangement. The carbocation skeleton has now rearranged because this carbon has shifted. This undergoes a 1,2 methyl shift in the rearrangement. So you need to watch out for these. If a carbocation can rearrange to form a more stable carbocation, it will rearrange. So if I can form a tertiary carbocation from my secondary that might initially form, it will happen, and that will lead to the major product. Now, if I have an SN1 reaction occurring at a carbon that is a stereocenter, the product at that center is a racemic mixture. So let's say this is the R. Once I form this flat planar carbocation, this is achiral, which means both sides of that carbocation are accessible. Because both sides can react, I can get the S enantiomer and the R enantiomer formed in basically a 1-to-1 mixture. It's a 50% chance it's going to come in from the left, to 50% chance it's going to come in from the right. And what I end up with is a 1-to-1 mixture of configurations at that stereocenter, which is a racemic mixture. So that one single carbo or stereocenter in this molecule actually ends up racemizing. And that's the stereochemical outcome for SN1s. So these mechanisms have been determined based on experimental evidence, right? People don't draw mechanisms just because they feel like it. They actually have to do experiments to figure out if the mechanism that is proposed is supported by evidence. So we asked some questions. What effect does the structure of the nucleophile have on the rate of reaction? Kinetics reaction, rate of reaction is a kinetics reactions. Those are critical reactions in determining what reaction mechanisms is happening in these various types of reactions. What about the structure of the alkane? How does that affect the rate of the reaction? What does the structure of the leaving group have on the rate of the reaction? And what is the role of the solvent? So all of these different types of questions are asked. Experiments are run. Again, we're looking at a lot of kinetics experiments. And then what we're going to do is make our generalized reaction mechanism based on the results. So there's something called nucleophilicity. Obviously, this has to do with the nucleophile. It's a kinetic property, and it's measured by the rate at which a nucleophile attacks a reference compound. And I'm using a standard set of experimental conditions. So what I'm trying to figure out is which nucleophile actually reacts faster, right? So here's an example. If I look at the rate in which a set of different nucleophiles displaces bromide ion from bromoethane, all of these reactions are done in ethanol at 25 degrees Celsius. This kind of looks like one of your labs this week, so sort of pay attention. So when I do this, I get some results. And what I know is these nucleophiles are much more effective, which means they react faster. These are moderate nucleophiles, and these are very poor nucleophiles. So negatively charged species are better nucleophiles than things that are neutral. But these negatively charged species also sort of had a dividing line. These are actually going to be stronger bases that end up being good nucleophiles. And then notice my sulfur, my fully protonated sulfur and nitrogen compounds are also considered moderate. It's those, so this is a whole bunch of neutral compounds, but they have sulfur and nitrogen atoms in common. These have the oxygen being the nucleophile, and when the oxygen is neutral, these end up being poor nucleophiles. So you kind of have to know this chart because the nucleophilicity, the type of nucleophile that's reacting, is going to help determine which mechanism the reaction is undergoing. SN1 reactions, remember, these are the stepwise where I undergo a carbocation. These are governed by electronic factors, namely the relative stabilities. Remember, this is my order of stability. The stability of the carbocation, which is an electronic feature, is going, because of that inductive stabilization, is going to determine largely whether something goes through SN1 or SN2. Now we're looking at the structure of the haloalkane, which is the substrate. And we're trying to figure out what that happens. So if I form a tertiary carbocation, which is much more stable, my energy of activation is lower because it's a more stable species, which means that the reaction rate is larger, it's faster. For SN2 reactions, this type of mechanism is governed by steric factors. So remember, the bond forming and the bond breaking happens simultaneously. So I have to look at how easily that nucleophile can approach the site of the reaction. How crowded is that carbon that bears the leaving group? And I have an opposite sort of order of reactivity here. If I don't have anything on the carbon, if I only have hydrogens, it's going to react much quicker because those other carbon atoms and carbon-based groups are going to block the site of reaction at that in that SN2 reaction, because that nucleophile has to come in from the backside, and that bond is forming as the leaving group is leaving. So we have to consider these two features. Just taking some coffee here. Okay, so let's look at these steric factors. Here I have a carbon that has a CH3 and 2 hydrogens. This has a primary carbocation or a primary carbon here. There is much less crowding, right? Notice this carbon is much more accessible to the nucleophile here. Here's my carbon in there. If I have a CH3 and I have another CH3 and another CH3, you can barely see this carbon, right? There's more crowding. Those methyl groups block access to the backside of that carbon that has that leaving group. So this is going to be much faster of a reaction, and this is going to be much slower because access, that backside attack, access to the backside of the carbon that bears that bromine is very crowded. It's sterically encumbered. It's not very accessible to that nucleophile. So what happens is that I have this effect, this competing effect between electronic and steric factors, which contributes to the competition between the SN1 and SN2 reactions. So anything that is primary or methyl never reacts by SN2. Anything that is tertiary never reacts by SN2. So if I have a tertiary alkyl halide, it will always undergo SN1 reaction. If I have a primary alkyl halide or a methyl, just methyl bromide, methyl iodide, it will never react by SN1 because remember, primary and methyl carbocations basically don't form. This is the case where I really have to look at other factors. Other factors like the nucleophilicity and the other stuff we're going to talk about is going to determine whether my secondary alkyl halides react via an SN1 or an SN2. So now let's look at the nature of the leaving group. The best leaving groups are iodine, bromine, and chlorine. These guys are such poor leaving groups. So this O minus, this RO minus, and the NH2 minus, they're very, very rarely, if ever, displaced in nucleophilic substitution reactions. These actually prefer to act as bases. So you're going to see them end up contributing much more through this beta elimination reactions. Iodine is the best leaving group out there, and that's because the greater the stability of the anion, the greater strength of that conjugate acid, right? So if I form, remember this goes back to REO, this is related to base strength. If my anion is stable, it will tend to leave better, right? I minus is very stable. HI is a very strong acid. I minus is a very weak base because it is so stable as an anion that it really doesn't want to react, right? So these atoms, which are much stronger bases, are going to rarely act as leaving groups. They will act as bases in beta elimination reactions, however. But they react as the base, not as the leaving group, right? So hydroxide is a very poor leaving group. But I can get this OH, if it's attached to a carbon and forms an alcohol, right? I can get it to act as a leaving group if I first protonate it with an acid. If I protonate that, what's leaving is water, right? Water is a neutral molecule. It is a much better leaving group than OH minus. So if I just take this alcohol, which is a tertiary alcohol, and I do not have any sort of acid in there, right? The OH is a very poor leaving group, and this substitution reaction will not occur. But if I have a strong acid that can protonate the OH group, what I'm forming here, right? This is being protonated. I'm forming this alkox, or what is that? This oxonium ion, right? The oxonium ion, which now can leave because I'm forming water, which is a stable molecule. That forms this carbocation because that water leaves, which means I can now add the chlorine as a nucleophile. So water is a good leaving group because it is a stable neutral molecule. Solvents. There are two different types of solvents. There's protic solvents and there's aprotic solvent. A protic solvent is something that contains an OH group. And remember, OHs can form hydrogen bonds. So I have an OH here, I have an OH here, here, carboxylic acids, alcohols. Those are really common protic solvents. As the polarity of the solvent increases, right, they become more protic. These solvents favor SN1 reactions. The greater the polarity of the solvent, the easier it is to form the carbocation, because the solvent can now solvate both the carbocation and the negatively charged leaving group. That stabilizes the intermediary species, which enhances the favorability of this reaction. Aprotic solvents, A meaning absence of, they do not contain an OH group, not a hydrogen bond donor. Aprotic solvents will favor SN2 reactions. So here I have dimethyl sulfoxide called DMF or DMSO, acetone, dichloromethane, DMF, which is dimethylformamide, is also a really good aprotic solvent that you'll probably see. So these solvents favor SN2 reactions. Even though they're polar, the formation of the carbocation is much more difficult than in that protic solvent because the anionic leaving group cannot be solvated. So that anionic leaving group can't be stabilized, which means that the SN1 is disfavored, which means in turn that the SN2, that simultaneously bond making and breaking, will be favored. So here's the key. When you look at a substitution reaction, you have to figure out, does it undergo SN2 or does it undergo SN1 by doing an analysis. First, I'm going to start at the haloalkane. If it's methyl or primary, SN2 is favored. SN1 does not occur. And then I can stop. I know what's happening. If it's tertiary, SN2 does not occur. SN1 is favored, right? And that's because of the ease of formation of tertiary carbocations. So when I have a primary or a methyl or a tertiary carbocation, I have a pretty easy decision to make if it undergoes substitution. Methyl and primary alkyl halides will undergo SN2, period. Tertiary will undergo SN1, period. This is the case where I have to do further analysis. If I have aprotic solvents and I have good nucleophiles, SN2 will be favored. If I have a protic solvent and I'm reacting with a poor nucleophile, SN2 is, or SN1 is favored. So if I have a secondary halide that is undergoing a substitution reaction, to determine whether SN1 is going to occur or SN1 is going to occur, I have to look at the nature of the solvent. If it's aprotic, it's going to favor SN2. If it's protic, it's going to favor SN1. I also have to look at the nature of the nucleophile. If it's a good nucleophile, it'll favor SN2. If it's a poor nucleophile, it will favor SN1. So this secondary requires much more analysis in order to figure out what's happening. Now, what about stereochemistry? If I undergo SN2, that concerted mechanism, the stereochemical result is inversion of configuration. The nucleophile attacks the stereocenter from the backside, the opposite side of the leaving group. That causes inversion. If I undergo SN1, that stereocenter gets racemized. The carbocation intermediate is planar, and I can attack from either side with equal probability. 50% comes in from the left, 50% comes into the right. That stereocenter becomes racemized. Okay, here's kind of the things that you're going to have to do in order to figure out how to predict the product. Here's some examples. Predict the product of each reaction. What is the reaction mechanism? Is it SN1 or SN2? These are all substitution reactions, and I want to pay attention to the stereochemistry. All right. This is a secondary alkyl halide, which has a stereocenter. This is my nucleophile. It's neutral and it's oxygen, which is a poor nucleophile. So this favors SN1. This is a protic solvent. This favors SN1. So SN1 is going to happen. So what I'm going to get is the ether, but I'm going to get the racemate of that ether because it's SN1. So I have to indicate the fact that I get both of these enantiomers because it's asking me to predict the stereochemistry. So this would be a racemic mixture. Okay. Primary alkyl halide, really good nucleophile, aprotic solvent, that all favors SN2. There's no stereochemistry there. So all I have to do is replace the bromide with the iodide. This is the nucleophile, the I minus. Boom, I'm done. Okay. Secondary alkyl halide that has a stereocenter. This is a really good nucleophile, these S minuses, right? This is the piece that actually is going to replace the bromide. So this favors SN2. Acetone is aprotic. This favors SN2. SN2 with a stereocenter is inversion. Oops, I did it again. Oops, I could just start singing Britney Spears, but I'm not. So I have inversion of that stereocenter. If I have hashed, I go to bold. If I have bold, I go to hashed. If I have S, I go to R. If I have R, I go to S. Now, this last one, so this undergoes SN2. This last one was a little tricky because this is also something that has to consider. This is the reactive center that has the leaving group. This is a protic solvent, which favors SN2. This is a really good nucleophile, which favors SN2. This is a secondary alkyl halide. So I am going to get backside attack. Backside attack. on that carbon. So what I'm going to get in my reaction, this has not changed, right? This has changed, and I'm going to get SH. That's my nucleophile, SH. Now notice this was cis, right? Up, up. This is still up. Backside attack means this is down. So now I get the trans. I can also look at this in this way. If I have the cis, I could just say this is going to be bolded, bolded. But if I invert here, what I'm going to get is bolded, because that didn't change, hashed, which now goes to trans. And then I could draw the chair knowing that those two were trans. So I could do it in this hexagon structure if that makes more sense. I know that initially that they're cis, they're both pointing up. So I'm gonna put bolded bromide, bolded tert-butyl. And then I know I have backside attack on that carbon that bears the bromine. That's gonna invert that center. So if it was bolded, it becomes hashed, which now gives me the trans molecule. And I can go ahead and write that in the chair configuration. So this is the kind of analysis that you're going to have to do on tests and quizzes. You have to be able to look at this. And this is why this chapter can be quite a learning challenge. You have to be able to analyze and know the chemistry for the substrate, the type of nucleophile, the type of leaving group, and the type of solvent, and using all of that information, put together what the most likely mechanism is, and then predict the product accordingly. So this takes practice. So make sure you practice. All right. I'll be back with elimination.